you mind if we record this session?
No, it's fine.
Okay. So, well, I just want to give you a very short, not an introduction, but to be very thankful with your time. I am also very thankful with Anna that called my attention to your work, and you are starting our seminar this semester. So this is the first one that we have for the second semester. So it's great. Thank you very much for your time, and you have 50 minutes, almost 1 hour to present us. Thanks.
Okay, thank you for having me. And don't hesitate during the presentation to directly ask your questions. And you don't have to wait until the end. Okay. Can you see the presentation or not?
Yes, I can see it.
Yes. Yeah.
Okay. Okay. Do you see it in full screen? Like, is everything okay?
Yes.
Okay.
Yeah.
So I'm gonna start with the presentation. So today I will present you EquiPy, which is a Python package implementing what we call sequential fairness and using some theoretical results of optimal transport. And this Python package, we implemented it last year between September and December with some colleagues at UQAM in Montreal, François Hu, Philippe Ratz, Arthur Charpentier, and Suzy Gondin. And this Python package implements the sequential fairness approach, which is a mitigation approach to avoid discrimination in your machine learning algorithm that was described in a paper accepted in a machine learning conference, AAI 2024. And this paper was written by François Hu, Philippe Ratz, and Arthur Charpentier. So just to begin with, I would like to give you the context of algorithmic fairness. So the notion of algorithmic fairness aims to have artificial intelligence systems that are based on predictive models that do not discriminate against some sensitive attributes, which could be ethnic origin or gender. And here, if we take the example of a machine learning model F, which predicts salary on a test set denoted y hat, and if we want to analyze the discrimination of this machine learning model regarding a single sensitive attribute, which is here ethnic origin and that we have access to in our data set, we can plot the densities, the distributions of our model predictions given the category of the ethnic origin, which are here Black or white people, and the graph is depicted on the right. And what we can see here is that the distributions for the two subsets, so Black people and white people, greatly differ. So it seems that our machine learning model F discriminates against Black people. And this type of discrimination can come from different sources. For example, it can come from the data. Indeed, because you train your machine learning models on usually historical data, you can reproduce the past injustices. Or you can also have in your dataset underrepresented minorities if your dataset is unbalanced. Moreover, the bias and the discrimination can come from your explanatory variables. Indeed, if I give you an example, even if you don't use the race or the ethnic origin as an explanatory variable of your machine learning model, you can still have other variables, which are called proxy variables, that are correlated with your sensitive attribute. For example, if you don't use the ethnic origin, but you use the address of your individual, because those two variables are correlated, because usually you can have neighborhoods with a majority of persons from a certain ethnic origin. And so if you use the address, you will be able to use the ethnic origin even if it was not an initial explanatory variable. And so, for example, in insurance, we usually use the address of insureds to predict some premiums. And so in this case, even if we didn't use the ethnic origin, we can still discriminate regarding this sensitive attribute because we use the address. And also the discrimination can come from intentional bias, which can be the result of deliberate choices, which can be benevolent or malicious. However, there is more and more legislation that prevents companies, for example, insurance companies, to use and to discriminate against some sensitive attributes when using artificial intelligence system. For example, we have the AA Act in Europe, a legislation from 2024, which aims to ban or limit AA systems in production that present an unacceptable level of risk. It means that, for example, they don't want predictive models to prevent some minorities to have access to credit loan. Also, in the insurance domain, we have some motor insurance regulation in the United States and in Canada, which is depicted on the right. So you can see here that in some regions of United States and Canada, insurers can't use some sensitive attributes, multiple sensitive attributes, to calculate their premiums. For example, they can't use gender and age. They can't discriminate regarding those two sensitive attributes. However, because of proxy variables, so explanatory variables that are correlated with your sensitive attributes, simply eliminating the sensitive attributes from the explanatory variables of your predictive models won't guarantee fair premiums in the case of insurance. So it means that you need an approach to evaluate and mitigate unfairness in your model predictions regarding multiple sensitive attributes, if you don't want to discriminate and if you want to respect the legislation. In the literature, until the approach of sequential fairness, there were multiple approaches to mitigate biases against a single sensitive attribute. But there was no methodology to do that regarding multiple sensitive attributes. And so this is the approach that I'm going to present you today, an approach that allows you to evaluate and mitigate unfairness in model predictions regarding multiple sensitive attributes. And so the objective here is to make your predictions fair regarding the sensitive attributes that you consider. For example, if we consider an insurance pricing model F, its predicted premiums Y hat and two sensitive attributes, which are here ethnic origins, A1 with white and black people, and gender, A2 with two categories, male and female. And on the left are depicted the predicted premiums for each of category of your sensitive attributes. And what you can see on the left is that your model predictions are really different when you consider only a category of your sensitive attribute. For example, for ethnic origins, the distributions of your predicted premiums for Black and white people are very different, and it is the same for gender. And one solution could be to choose a reference category and to transform all your predictions to this reference category. For example, you could move all your Black individuals into white one and all your female individuals into male ones. However, here we avoid to select a reference category because if we use Black and female as the references, the total premiums would fall short of the planned amount needed to cover claims. And on the other hand, if we use white and male as the references, the premiums would exceed the planned amounts, leading to higher costs for the insurers. So here in this example, it is important that we preserve some characteristics of our model predictions. And it is why we don't want to select a reference category, but we want to find an in-between distributions from our different categories of our sensitive attributes. And so the mitigation approach, the sequential fairness approach, will try to find this in-between distribution that avoid discrimination in your model predictions in order to be fair regarding, for example, ethnic origin and gender.
Agathe, may I
Yeah.
ask you a question?
Yeah, sure.
Since you are moving to maybe your proposed solution, I was wondering, what is your definition of discrimination? Because so far what I see is that if your model is sensitive to a variable, then you call that discrimination.
Sorry, can you repeat, please? I didn't hear the
What
end.
is your definition of discrimination?
Oh, okay. So here, I mean, I will give you the definition of the fairness metric that I will use in the next slides. But here it's more like an intuition. I can't assure you that my model is fair or unfair because I didn't define a fairness metric, but I can see when I plot the densities of my predictions for each group of my sensitive attribute that they are really different. And what we can see here is that, for example, the predicted premiums are lower for Black people than white people, which is clear here. And so I have the intuition that my model is unfair. And I would like to correct it. But I will give you the fairness metric later. And actually, the fairness metric that I will present you is based on this comparison. You want the distributions in your different categories of sensitive attributes to be the same. So here we can see that it's not the same, and so our model is unfair. I don't know if it answers your question.
Yes. Well, I mean, if you take the first example you gave, white people have more a predicted value of wages which is higher than Black people.
Yeah.
So I wonder, I don't know, why is that discrimination? If that's the case, I mean, there must be some benchmark, some way of, if you have a data set that it's like that for some reason, I don't know.
Okay.
Then yeah. So why
do I have this discrimination?
Why do you call that discrimination? I mean,
okay.
Here between black and white and premiums, I guess I understand, but there is some cases in which just the fact that there is a sensitivity to your variable.
Yeah. Yes, for example, there could be some variables. So here are just simulations. So it's not a real data set. But one way that we could explain this discrimination and why I call it discrimination here is because I say that it is discrimination because I consider ethnic origin as a sensitive attribute. Even if there are some factors or explanatory variables that could explain why white people have much higher predicted premiums than Black people, I want to call it discrimination because the legislation prohibits me to discriminate against Black or white people. I'm only answering to, for example, the legislation.
Okay,
I
okay.
need, yeah. Is it clear for others?
Yes, it is clear.
Okay. Yeah, just to clear this point here in the presentation, I will always consider some sensitive attributes, and the choice of those sensitive attributes is not mine, like is not the choice of the data scientist. I just answer some sort of legislation that prohibits me to discriminate against those sensitive attributes. And so I just want to make sure that my model predictions are fair regarding this sensitive attribute. But I don't choose which sensitive attributes I need to consider. Okay, and so here the objective was to prevent discrimination regarding multiple sensitive attributes and not a single one, because as we saw in the motor insurance regulation, sometimes you need to consider multiple sensitive attributes in the same time. And because there already exists some mitigation approaches to avoid biases regarding a single sensitive attribute, we could simply cross the categories of our multiple sensitive attributes, for example, gender and ethnic origin, and define a new single sensitive attribute. So above here, you have the different crossings that we would obtain if we consider two sensitive attributes, gender with female and male, and ethnic origin with white and Black. And so here we obtain a new single sensitive attribute with 4 categories: female and white, female and Black, male and white, and male and Black. And so because now we have a single sensitive attribute, even with 4 categories, we can apply the approaches that exist in the literature to mitigate the discrimination, if there is some in my model predictions. However, you can see here that when you have more and more sensitive attributes, you will have multiple categories, and also it will become more difficult to interpret the mitigation approach and the results that you obtain, the transformations in your model predictions. And it is why François Hu, Philippe Ratz, and Arthur Charpentier thought about a sequential fairness approach, which is more interpretable across your multiple sensitive attributes. So here you take your initial model prediction, y hat, and you will first correct and transform your predictions to obtain predictions fair regarding A1, which is here the ethnic origin. And you will take these model predictions that are fair for ethnic origin, and you will transform them in a second step to make them fair regarding gender. So you will do it sequentially. You will transform your predictions sequentially to obtain final predictions that are fair regarding both your sensitive attributes. And so here you can see that you need to define an order in your sensitive attributes to apply the sequential process. However, we will see in the next slides that the order doesn't really count for the final results. And compared to the intersectional fairness approach, the sequential fairness approach allows for easily adding sensitive attributes to meet the changing regulatory demands. For example, if the regulators prohibits you to discriminate in the past against gender and ethnic origin, and now they also ask you to not discriminate regarding age, for example. In the case of intersectional fairness, you will need to go back to your initial model predictions and to define your new single sensitive attribute by crossing not only ethnic origin and gender, but also age, with the categories of age. Whereas in the sequential fairness approach, you will be able to just take your model predictions that are fair for ethnic origin and gender, and you will only need to correct them regarding your new sensitive attribute, which is age. So it is easier to do that for sequential fairness to add new sensitive attributes. Okay, and so now I just finished the introduction, and now I would like to give you more theoretical results about the sequential fairness approach. And first of all, I will give you the fairness metric that we use to quantify if there is discrimination or not in the model predictions. And if we observe that the fairness, that our model predictions are not fair, given our fairness metric, we will want to mitigate the unfairness in our model predictions by using the sequential fairness approach that I will present after. And finally, I will give you an example in insurance of application of the Python package EquiPy. So to begin with, I will give you some notations for the following of the presentation. So we have a matrix X with non-sensitive features that we consider non-sensitive. Then we also have a matrix A that contains multiple sensitive attributes. We also have our response variable, y hat, which can be continuous or scores from a binary classifier. We also have a predictive model f on x and I, with f star denoting the optimal bias estimator. And we also need to denote nu f, the distribution of our predictions, with the cumulative distribution function capital F and the quantile function capital Q. And for the following, we also need to define nu f AI, which is the conditional distribution of our model predictions only in the subset where a sensitive attribute, capital AI, takes the value AI, with the cumulative distribution function and the quantile function associated. And here we will also denote RF, a risk metric, which here is the mean squared error. And so now I am going to present you the unfairness metric that we used and that is developed in the EquiPy Python package to evaluate the unfairness in your model predictions. And here, the unfairness metric that will be used is called demographic parity. And demographic parity requires that the prediction made by your model need to be independent of your sensitive attribute A, which can be race, gender, or age. And with this definition, we can define strong demographic parity. And for strong demographic parity, you want your distributions regarding the values that can take your sensitive attribute to be equal, or the distance between those distributions to be equal. For example, if you consider your sensitive attribute to be gender with two categories, male and female, you want the distribution of your model prediction in subsets male and in subset female to be the same. Or, in other words, the distance between the distribution of your model predictions in subset male and the distribution of your model predictions in subset female to be equal to 0. So here you consider the differences in distributions in each subset. But you can also, you can rather consider the difference between the distribution of your model prediction in each subset and your overall distribution of your model predictions, which is here the definition that we will use. So we said that F is strongly fair regarding a single sensitive attribute AI if and only if the maximum distance between your overall model predictions and the distribution of your model predictions in each category of your sensitive attribute is equal to 0. And we will extend this definition to the case of multiple sensitive attributes by only summing the different unfairness metric regarding each of your sensitive attributes. And here you can see that to be able to compute the unfairness metric, we need to define a distance between probability distributions. And so here we will use the Wasserstein distance from optimal transport theory to compute the unfairness metric. And so I would like just to give you an example of how to calculate this unfairness metric. So here we will calculate the strong demographic parity for two sensitive attributes, ethnic origin A1 and gender A2. And both of those sensitive attributes contains two categories, black and white for ethnic origin and female and male for gender. And so the first definition that I gave you is represented on the graphs on the left. So you have your distributions of your model predictions in each subset of your sensitive attributes. Above, you have the distribution regarding your ethnic origin, and below, you have your distributions regarding gender. And in each case, you will calculate your unfairness first for ethnic origin by computing the distance between the two distributions, for Black and for white people. And in the case of gender, you will calculate the distance between the distribution of your model predictions for female and for male people. And the global unfairness of your model predictions will be simply the sum of your unfairness metrics for ethnic origin and gender. But we will prefer another definition of unfairness. Here, rather than computing the differences between distribution of your model predictions in each subset of your sensitive attribute, we will compute the distance between the distribution first for Black people and the overall distribution, which is denoted D1, and the distance between the distribution of your model prediction for white people and the overall distribution with all your predictions. And we will simply say that the unfairness for ethnic origin is the maximum between the distance D1 and the distance D2. And we will do the same for the gender sensitive attribute. Do you all understand how we can calculate this unfairness metric? Is it clear, or do you want me to explain another time maybe?
For me, it's
For
clear.
me, it's clear. Yeah, for me too.
Okay. Okay, great. Okay, so as I said earlier, to be able to compute our unfairness metrics, we need to define a way to compute the distance between two distributions. And for that, we will use the Wasserstein distance, which comes from the optimal transport theory. And so here I would just like to give you some results about optimal transport theory, so you will be able to understand what the Wasserstein distance is. So first of all, the objective of optimal transport is to minimize the overall cost of moving one distribution, one probability distribution, onto another one. So, for example, in our example, in the previous example, we could want to move the distribution of model predictions of Black people onto the distributions for white people. And so we would like to find the most efficient mapping to do that, so to transform one distribution onto another one. And this mapping is denoted T, and it will tell you how to move each individual of your distribution nu A into individuals of your distribution nu B. And we will solve the problem, the optimization problem that is depicted here. And if we consider a convex cost C and univariate distribution UA and UB, we have a closed form solution, a closed form formula for the optimal transport map denoted T star, which is simply the quantile function of nu B composed to the cumulative distribution function of nu A. And so just to explain a little bit, I depicted a graph on the right. So consider that you have two distributions, your predicted salaries for Black people and the predicted salaries for white people. And here you have two Black individuals, the points on the graph. And you want to move those two individuals, those two Black individuals, into the distribution of predicted salaries for white individuals. And if you use the optimal transport map T star, you will simply need to calculate the level of quantiles of your two individuals in the Black group, and you will assign to them the same quantile levels of the white group. So, for example, for the first individual, we know that its quantile level in the Black group is 10%. And so you will transform them onto the right distribution by simply regarding which is the quantile of level 10% in the distribution of the model predictions for white people. And you will give him this value. And this approach allows you to preserve the order of your individuals before and after transformation because you use quantile. And so the optimal transport map was the most efficient way to map your individuals from one distribution onto another one. And the Wasserstein distance is the overall cost to do that. So the overall cost to transform a distribution onto another one. And so it is a measure of distance between two distributions, UA and UB. And for univariate distribution, the Wasserstein distance is defined as the integral over your quantile function over the absolute difference of your quantile function for your two distribution. And that's what I represented on the right. It is the one Wasserstein distance. So here are depicted the quantile functions of model predictions for First, Black individuals, and second, white individuals. And here, the Wasserstein distance is simply the area between those two curves. And so it measures the distance between the distribution of model predictions for Black people and for white people. And that is the distance we will use to compute our unfairness metric. So we will say that our model is fair regarding a sensitive attribute AI, which can be gender or ethnic origin, if the one Wasserstein distance between the overall distribution of your model predictions and the distribution of your model predictions for male and for female to be equal to 0. So you want the maximum value to be equal to 0. And you will need to compute the Wasserstein distance for all of the categories of your sensitive attribute. Okay, so now that I have defined the unfairness metric that we want equal to 0 if we consider that our model predictions are fair regarding some multiple sensitive attributes. But if we observe that our model predictions are not fair regarding our multiple sensitive attributes, we would like to apply a mitigation method to transform our model predictions into fair ones. And I will present you the mitigation approach, which is called Sequential Fairness and which was implemented in the Python package EquiPy. So just to start with, I would just like to remind you the objective here. So we would like to transform our model prediction fxa into fair ones, which are denoted fb. But here we would like to preserve good performance. Indeed, we are going to transform our model predictions, and usually we will select the ones that are the more accurate or that maximize some performance metric. And if we transform them, we might lose some performance. So by transforming them, we would like to minimize this performance loss, which will be calculated thanks to the risk metric RF. And there exists multiple methods to mitigate to avoid discrimination in a machine learning algorithm. First, you can use pre-processing methods. So in this kind of method, you will transform your multivariate distribution of your explanatory variables into a fair explanatory variables, and then you will apply your model. And that will normally give you fair predictions. You can also use in-processing methods in which you will add a fairness penalty in the objective function while you are training your machine learning model. And then we have the post-processing methods. So here we will directly transform the univariate distribution of our predictions, of our model prediction y hat. So this last type of methods is interesting because we are not changing our machine learning model. We are only impacting the predictions of our machine learning model. So we don't need to train another time or to change the training of our machine learning model. And the EquiPy methodology, this sequential fairness approach, is a post-processing method. And so now I am going to present you this approach. And so still using some theoretical results of optimal transport theory, we will make our model predictions fair by using the Wasserstein barycenter. And the Wasserstein barycenter is what we can call an in-between distributions, so to compute it, we need to solve an optimization problem, once again, and we want to minimize, given some weights, the two Wasserstein distance between some groups in our model prediction and the overall model predictions. And that's what I depicted on the right. So here we can consider that K, capital K, is equal to 2. So we have two different distributions: the model predictions for female and the model predictions for male. And here we would like to find the in-between distribution, what we call the Wasserstein barycenter. So we need to find the in-between distribution that satisfies the minimization problem. And actually, they selected the Wasserstein barycenter to find the in-between distribution because it allows you to achieve unfairness, so to have an unfairness metric equal to 0, while minimizing the performance loss. And so that it is a really interesting property because, for example, in companies, if the legislation asks you to not discriminate regarding some sensitive attributes, you would need to transform your model predictions if they are unfair, but you don't want to lose too much performance with your machine learning model. And so the Wasserstein barycenter, allows you to do that. And it also allows you to keep the global average of your model predictions before and after transformation, which can be interesting, for example, when you work with insurance premiums. And so now I am just going to give you the different formulas that allowed us to compute the mitigation approach. And I will start with the mitigation approach for a single sensitive attribute, because the approach for multiple sensitive attributes just extend these results. So here we have a sensitive attribute, A1, with multiple categories, and we want to compute the distribution for each of those categories for the model predictions that are fair and that are denoted FB. And so we will find the distribution by minimizing the optimization problems by taking weights as empirical frequencies for A1 in your dataset and by computing the Wasserstein barycenter. And so the formula for your model prediction FB is the composition of quantile functions and cumulative distribution function for the different subgroups of your model predictions given the categories of your sensitive attribute. And so here we have a closed form solution to compute it, to transform your individuals to attain fair prediction regarding your single sensitive attribute. And we implemented this approach in the EquiPy package in a function called fair Wasserstein. Okay, so I know that the formulas can be quite difficult to understand, but I'm just going to give you an example in the next slide. So here we consider a machine learning model prediction, y hat, which is defined on our explanatory variables that are non-sensitive, A, and the value A1, corresponding to our sensitive attribute, which is here ethnic origin, and we have two categories, white and black. And so to apply the mitigation approach that I just showed you, you will take first your individuals in your white subgroup. And you will transform the model predictions by applying the formula above. So you will first take your initial model predictions for white people, and you will multiply it by the empirical frequency of having white people in your dataset, and you will add the empirical frequency of having Black people in your dataset, multiplied by the optimal transport formula applied to white people to transform them into Black people, because you have the composition of the quantitative function and the cumulative distribution function. And so this formula allows you to transform the model predictions of your white individual. And now you need to do the same for the Black individuals by using the same kind of formulas. And so here are the solutions of the minimization problem with the Wasserstein barycenter when we have a single sensitive attribute with two categories, white and Black people. So we simply applied those formulas in the EquiPy Python package to make the model predictions fair regarding a single sensitive attribute. And so now I am going to extend the results of the mitigation approach for a single sensitive attribute to the case of multiple sensitive attributes. For example, two, like ethnic origin and gender. And it is the sequential fairness approach. And to compute it, to transform your model predictions, you will simply compose the fair predictors for each single sensitive attribute. So you will use the formula that I presented in the previous slide for a single sensitive attribute, and you will calculate it for each of your sensitive attribute and then compose them. So what you can see here is that you need to define an order to sequentially correct your model predictions. And so you need to specify an order in your sensitive attributes. However, in the paper of Sequential Fairness, the authors proved the associativity of Wasserstein barycenters, which means that regardless of the order that you choose to sequentially correct your model predictions, your final predictions will remain the same. And the approach with the multiple sensitive attributes is implemented in the function multi-Wasserstein of the fairness model of EquiPy. And so I am going also to give you an example, so how we calculate the mitigation approach for two sensitive attributes. So here we have a model predictions, y hat, that we corrected regarding ethnic origin with the formula that I presented you earlier. So it is this one. So this formula allows us to get model predictions that are fair regarding ethnic origin. And we will get FB1. And so we will take those model predictions that are fair regarding ethnic origin, denoted FB1, and we will make them fair regarding the second sensitive attribute, which is gender, with two categories, male and female. And so to now make those model predictions FB1 fair regarding gender, we just need to apply the same formula that we did earlier, but now for the sensitive attribute gender. And we will apply it not to our initial model predictions, F, but to our model predictions that are fair regarding ethnic origin, what we did in the previous step. And so here are the same formula that we saw earlier, except that we take FB1, the model fair regarding ethnic origin, and not F, the initial predictions. And we will do that sequentially. It's always the same formula, just not applied to the same model predictions. Okay, is the mitigation approach clear, or would you like me to go back to some slide in the presentation?
Agathe, I have a question.
Yeah, sure.
I understood that this is a definition of fairness which is stronger than equal parity, right? So
can you repeat, please? Sorry, I don't hear well.
I understood that this is a definition which is stronger than equal parity, right? Or equal something. I don't. How do you call the first definition of fairness?
Equalized odds, maybe you.
No. The one that demographic parity.
Yeah.
Okay. So yours is more stronger, right?
Yeah.
So this definition has the virtue, has of the fact that if I use a randomized classifier, I'm not going to succeed. Okay, that's the problem with demographic parity. That if you randomize, you can actually be fair.
Yeah. Okay.
With yours, you can't, because obviously you introduce this distance between the population and the conditionals, which is very nice. But how does this guarantee the fact that you use Wasserstein measure to sort of find a barycentric distribution, which is close to the conditionals? How does this guarantee that you don't lose performance in terms of root mean square error, in terms of the risk that you defined at the beginning?
Okay, so if you suppose that, okay, I'm just going back to this slide. Okay, if you suppose that your initial model predictions that you obtained thanks to your machine learning algorithm were optimal regarding a certain performance metric, which can be the mean squared error. And to achieve fair predictions, so to make your unfairness metric equal to 0, you will transform your predictions. So if initially they were optimal regarding a performance metric, you will always lose some performance. And so there is always a cost of making your predictions fair. However, some theoretical results will tell you that you will lose performance by making your model predictions fair, but using the Wasserstein barycenter will be the way to lose the less performance possible. Does it answer your question, or you will always lose performance?
Yeah, and it doesn't matter the risk measure you use?
Yes, actually, this is true. Those results are true for accuracy and mean squared error. But it wasn't proved for example, F1 score. That the Wasserstein distance will allow you to lose the less performance possible.
Okay, great, thanks.
Okay. Is there any other questions about the mitigation approach? Maybe it will be clearer when I will present you the illustrative example, but if you have questions now, don't hesitate to ask me. Okay, so I will just finish with an illustrative example of dataset in life insurance, in health insurance, and I will present you the application of the Python package EquiPy. So we will use the life insurance dataset that is available online, the SEER database, and we will try to predict the 1-year mortality of US individuals with melanoma skin cancer. And so we have approximately 500,000 individuals from 2004 and 2018, in the United States. we have different explanatory variables. We have 16 features, some describing patient characteristics such as age, gender, ethnic origin, and some cancer attributes like the tumor size or the extent of the tumor. And with this dataset, we consider two sensitive attributes: gender, which has two categories, male and female in our dataset, and ethnic origin, which here has 5 categories. So in this case, we are in the multiple sensitive attributes framework. So we will use the function multi-Wasserstein that implements the mitigation approach called sequential fairness for multiple sensitive attributes. Before applying the EquiPy package, we first need to model our binary response variable here. And so first, we split our dataset into a train and a test set. Then we fit our model. Here we used a logistic regression model. And then we apply this model F on the test set to obtain y hat on the test set. And so for now, we didn't apply the EquiPy pattern package. We simply did the model fitting. And here I would just like to give you an example of the problem of the proxy variables. So here I fitted two different models. The first one that includes the sensitive attributes ethnic origin and gender in our explanatory variables, and the second one that don't include the sensitive attributes as explanatory variables. So the first row of the table that is depicted here represents the performance metric and the unfairness metric that we get when we don't use ethnic origin and gender as explanatory variables of our machine learning model. And the second row is the one where we included the sensitive attributes. And so here you can see that when you include your sensitive attributes, you have an unfairness metric that is higher than when you don't include the sensitive attributes in your model, meaning that your model discriminates more when you include your sensitive attributes, which is logical here. But I just wanted to show you that when you don't include your sensitive attributes in your model, you still have an unfairness of 0.21, 0.22 approximately. So it is just an example that even if you remove your sensitive attributes, ethnic origin and gender of your explanatory variables, you still get unfairness in your model predictions. So this is not an efficient way to deal with discrimination. And what is also important to note here is that we decided to fit a logistic regression model here, but we could have fitted any other machine learning model because EquiPy, the sequential fairness approach, is a post-processing approach. So it doesn't depend on the model that you used. It will simply transform your model predictions. And for the following of the presentation, we will consider the model, the logistic regression model, where we included both sensitive attributes as explanatory variable. Okay, so once I have fitted my logistic regression model on the test set, I need once again to split this test set into two sets: a calibration to compute the different cumulative distribution function and quantile functions that appear in the formula for the mitigation approach, and a test set to apply the mitigation approach. And as I said earlier, we need to define an order to sequentially correct our model predictions. So here we will first correct for ethnic origin, A1, and then for gender, A2. But the order doesn't count for your final predictions. If we had chosen to first correct for gender and then to ethnic origin, we would get the same final fair predictions. The third step is now to fit and transform your test predictions using the multi-Wasserstein function from the fairness model of EquiPy. And so below, I depicted one graph that you can obtain with EquiPy package once you, and to follow the sequential steps of your model, of the correction of your model predictions. So the first graph is your initial model predictions that we differentiated regarding your ethnic origin. The second graph is the distributions you get when you correct your model predictions for origin. And the last one is the distributions you get of your model predictions when you correct for gender. And what we can see here is that the second graph shows you that the EquiPy Python package finds an in-between distribution to be more fair regarding origin. And then when you correct regarding gender, you don't really change your distribution. Okay, and so we can also plot other graphs with the EquiPy Python package, which are called fair waterfall plot and fair multiple arrow plot. And those graphs allow you to see the relationship between unfairness and metric and performance metric. The first graph on the left is called fair waterfall plot. And here you will be able to see the gain in fairness of your model predictions when you correct regarding your multiple sensitive attributes. So the first bar corresponds to your base model predictions, where you had an unfairness of 0.27. Then you will correct your model predictions regarding A1, which is ethnic origin, and you will go down, you will decrease your unfairness to 0.7. And then you will correct your model predictions regarding gender, and you will get an unfairness metric of 0.05. And that will be the global and the final unfairness metric of your model predictions that you can consider fair regarding ethnic origin and gender. And on the right is depicted the fair multiple arrow plot graph, which is also a graph that you can compute using the EquiPy Python package. And here the graph is different because you are able to see the fairness performance relationship for all the possible pathways to achieve fairness. Here you have two sensitive attributes. And in the multi-Wasserstein function, you need to specify an order in your sensitive attributes. So here we decided to first correct for ethnic origin and then to correct for gender. But on this graph, on the graph on the right, you also have the pathway to fairness for the order, gender, and then ethnic origin. So on this graph, all the possible orders are depicted, and you can see how you lose unfairness and how you lose performance during your sequential corrections. And it is important to note here that the final point of this graph, which is the red star, once your model predictions are fair regarding both your sensitive attributes, regardless of the pathway that you took, so first gender and then ethnic origin, or first ethnic origin and then gender, you get to the same point, which was one of the results of the paper of Sequential Fairness. So here are the graphs that you can obtain thanks to the EquiPy Python package. Maybe I could just show you how to use it on a notebook if we have some time left, because I arrive at the end of the presentation. So I will just show you how it is possible to use the EquiPy Python package in practice. So first you need to do your Python imports, and you also need to import the package EquiPy. Then you just import the data. So here is the data I presented you with, which try to predict the mortality rates of individuals who have melanoma skin cancer. So here are the first 3 rows of your data set, so with the different explanatory variables, and D is the response, the binary response variable, and you also have sex, so one of your sensitive attribute, and also origin, the other sensitive attribute. So first you will apply your logistic regression model that by transforming by one hot encoding your categorical variable, split your data set into 3 sets: train, calibration, and test sets. The calibration set is used for applying the EquiPy Python package. So you train your logistic regression model, and then you predict it on both calibration and test sets to apply the EquiPy Python package. So here are some performance metrics of your initial model predictions. So the accuracy is great, 0.99. You have not a great recall or F1 score because of the unbalanced data set. You have your confusion matrix here, and then you can apply the package EquiPy. So the EquiPy package contains 3 models: metrics, fairness, and graphs. And in each module, you have your different functions. So in the metrics module, you have the function performance and unfairness to compute the performance metrics and the unfairness metrics. In the fairness module, you have the functions of multi-Wasserstein to transform your model predictions. And then in the graphs model, you can visualize the relationship, for example, between fairness and performance. And so to transform your model predictions, you simply need your model predictions and also the different values for your observations of each of your sensitive attributes, which are here, origin and sex. And to apply the EquiPy Python package, you first need to create an instance of the multi-Wasserstein class, and then you will fit the model, the mitigation approach on your calibration set, and you will apply the quantities that you find by transforming your test predictions. And you will obtain, in a simple way, your final fair predictions. And thanks to the metrics model, you are able also to see the gain in fairness that you achieved by mitigating your model predictions. For example, before the mitigation, I had an unfairness of 0.24, and the unfairness decreases to 0.05 when I apply the EquiPy Python package. We can also compute the accuracy or the F1 score, so all the metrics that you can find in the sklearn package before and after mitigation. And we can see here that for the accuracy, we don't lose too many performance, but in the case of F1 score, it decreases a little when we mitigate our model predictions. And an interesting thing that you can also have with the EquiPy Python package is that you are able to have the different step of correction. So, for example, you will have your initial model predictions, and even if you correct regarding two sensitive attributes, you can still see the transformed model predictions when you first correct regarding origin and then when you correct regarding sex. And you are also able to see the decrease in unfairness at each step of correction. And here is one of the graphs that you can obtain with the function, for example, for density plots.
Agatha,
Yes.
can we just try to wrap up in 1-2 minutes, please? Because we are already 50 minutes.
Okay, yes, no problem. Yeah.
I have a question, Agatha. Sorry if I can interrupt right now.
Yeah, go on. Yeah.
Agatha, in the EquiPy package, it's possible to use another definition of fairness. For example, you're explaining about demographic parity, but for example, if I want to use equalized odds or equal opportunities, is it possible to change the measure of fairness?
No, actually, we only implemented the calculation of the demographic parity.
Okay, I got it. Thank you.
Thank you.
I have another question, sorry.
Yeah, no problem.
What would happen if we consider all the features as sensitive features? Like, would that have a negative effect?
I didn't try it, but I guess that actually your model will lose a lot of performance if you because you will it means that your final model predictions will be independent of all your explanatory variables. So I guess it would maybe resemble to a randomized model or something like that.
Okay. What I'm thinking is that it is difficult to select which features are sensitive attributes and which ones are not. Like, for example, in the countries, the third slide you showed, I think that there was credit history. Like, can credit history be considered as a sensitive attribute? Or, like except legislation.
So in certain states you can't use the credit history because in the past there was some discrimination with credit history. Some minority groups were not able to have access to credit loan. But yeah, it can be difficult to select the sensitive attributes, and it is why usually I guess you can only take the ones that are forbidden with the legislation.
Yes, it could be. That's the best solution.
Yeah.
Okay. Thank
you. And also because I know that when you work in the company, the performance is really important, for example, in insurance, but in any other domain. And the more sensitive attributes you consider, the more performance you will lose. So I guess that the companies don't want to lose too much performance, so they will only select the sensitive attributes that the legislation gives them, maybe.
Okay, thank you.
Yeah, so yes, I can just finish in 2 minutes. I just wanted to tell you that here in the example I showed you, we were applying exact fairness. So it means that our final unfairness metric of our model prediction is equal to approximately 0. But it is also possible to prioritize your sensitive attributes by, for example, you can want to have exact fairness in origin, but approximate fairness in gender. Because actually, in our example, when you make your predictions fair for gender, you lose some fairness for origin. And it is something that you can do by adding an argument in the transform function of the EquiPy Python package. So you can have approximate fairness. And it can be also useful if you see that achieving fairness make you lose a lot of performance for your machine learning model. So you still want to achieve some fairness, but you don't want to lose too much performance. So you can actually use approximate fairness to do that. Okay, and so just to conclude, so I just presented you the sequential fairness approach that allows you to calculate unfairness metrics of your model prediction and also to mitigate your model predictions to be fair regarding not a single sensitive attribute, but multiple sensitive attributes. And this is what is implemented in the Python package EquiPy, which is easy to use because you just need to give it your model predictions and the data frames, the data sets with the sensitive features that you consider, but you don't need to train your model all over again. And you can actually apply it to any machine learning predictions that are continuous. Okay, so thank you everyone, and don't hesitate if you have other questions or even if you have some comments, or if you would like to use the package, you can send me email or look at the documentation also.
Agathe, I think it was great. Thank you very much. The only problem is that I have to leave, so if somebody wants to stay and keep maybe taking questions, that would be great. And but it was a very, very nice seminar. Thank you very much, and for sure I'll check the package.
Thank you for having me. Thank you.
Okay, bye. Anna will take care of any questions and answers in case somebody wants.
Yeah. Okay.
Yeah, thank you, Agathe. Honestly, it was so amazing. I didn't see the last part of the presentation, the application, and I really enjoyed seeing how we can do that in practice. So thank you. Maybe if some of you are interested, I think we can like put this script on the cloud or something. Do you think so?
Yeah. Actually, I am going just after the presentation to put the codes on GitHub. And so I am going to put the link in the presentation, and I think I need to send you the presentation so you can have it. And you can have all the information that you need, and also my email address if you need to ask me some questions about the presentation.
Perfect, nice. Does anyone of you have some questions or? Well, again, thank you for everything again. I think it was very, very nice to have you here, and yeah, to see one of these applications. So yeah, have a good day.
Thank you, and thank you